Okay, I hope you are still able to hear me. Okay, okay. So, if I recall correctly, so by the way, welcome to week 5. Okay, so I think if I recall correctly, I had just not done one step. Let me just check which direction I did. I think about it. Okay, so the question was prove that null space of AA transpose is null space of A transpose. So the proof we had only shown one direction, which was null space of AA null space of A transpose is null subset of null space of A transpose. We had shown this, and I had just asked to check the other side, which is that null space of AA transpose is a subset of null space of A transpose. So the reasoning is actually very simple. So let's just start with this. So let's say you are given A transpose AA transpose X is 0. All you need to do is you just need to multiply by X transpose. Okay, because it's a norm, this is if and only if AX equals to 0. Does that make sense? Sorry, AA transpose. Sorry, that's a mistake from my side. Null space of A. So that's it. This is it. Hopefully this is clear now. Yeah, it was a really long way to do it, and I don't think I quite understood. I don't think need to appeal to those results, because for that you will need to then prove all those things. So, all right. You people had asked me to try some questions from Boyd. So I have tried a few questions. So we can do that. But just before we start doing this, like I was saying last time, maybe a few linear algebra things for revision, and then we can proceed towards this question. Okay. So just to brush up our linear algebra a bit, see a few more results. So, okay. So the claim is n cross n matrix has n linearly independent eigenvectors then it is diagonalizable. So how to do this? Any thoughts? So just for simplicity, let me give the names. Let's say v1, v2, vn are the eigenvectors of A. Okay, and they are all linearly independent, all of them. So what can we do in this situation? So what does it mean for a matrix to be diagonalizable? Okay, So there are a few assumptions that you said, but in the simplest form, what we mean is this. Sorry, P. I mean, doesn't matter. P, PD, P inverse, whichever way we put it. Where P is obviously invertible here, and D is a diagonal matrix. Okay, this is what we mean by diagonalizable. So what I am trying to say is, let's say if you have n linearly independent vectors. Does this have a pointer? I think not. Okay, anyway. So what we'll do is, let's just take any vector that, because these vi's are linearly independent, we can just take a linear combination of them. We'll get a new vector x. Let's just see what x is doing, what a is doing to this vector x. So we're just applying the definition of the fact that vi's are the eigenvectors of A, which will give us alpha I, lambda I, vi, where lambda i's are the eigenvalues of A corresponding to the eigenvectors vi. So in essence, what we have, I'll just rewrite this a bit again. So I'm just putting it as a matrix. This is a diagonal matrix with diagonal entries as lambda i's, and the rest are 0 entries. And this is my vector alpha 1, alpha n. So this I'll call P. So what I mean is A times, so by the way, here this can be written as same matrix vector product. So this matrix times the vector. So what I can say is, I can just put that instead of A times x, and I can then put a look at this side, this side. So I just put that here. Okay, so this is my matrix, this is another matrix. This is going to be my D. So what have I done? I have so this is P, just to reiterate. So what I have written here is AP times some alpha vector is equal to PD times some alpha vector. This is some matrix that I have highlighted here, AP and PD. So it's something that you can just write it down. It's a very simple proof. If AX equals to BX for all x, this is same as saying A is B. Okay. So what we have proved here is AP is PD, and note that P is invertible. Why is that? Yeah. So A is PDP inverse. Okay, so this is that's all I wanted to say. So okay, so just one more step maybe. So why diagonalizable? Because I can apply operations, linear transformations to A such that I can make it diagonal. So D equals to P inverse AP. So why by the way do we care about this diagonalizing? So okay, the very simple reason is you want to solve Ax equals to B, right? If I say, let's just take a 2 cross 2 case. So if I have my matrix A as this diagonal matrix, where we assume that, let's say, a1 a2 not 0, a1 a2 not 0, then x1 x2 to solve is decoupled. The problem is decoupled now, right? So what I am having is, for my x1 I just care about this a1 and b1. It's just a simple scalar multiplication to find out what the value of x1 my system solution is. And similarly for x2 I only need to care about this entry. So I have decoupled. There's no interaction between x1 and x2 here. So this p1 by a1 and this is p2 by a2. So if we can, so what coming back to this point, which is this. So if I know, if see that this d here, this d is something that is just a diagonal matrix, so I can solve the solutions in this straightforward manner because it's a diagonal matrix. I can just plug in here. I already know the p's, they are the eigenvectors of A, so I can easily find the corresponding solutions for A. Is that fine? Okay, so yeah, by the way, if these are all known and straightforward, I can move to other things, but there are just some basic things which we'll keep on using again and again, so better to revise. Okay, so one more thing that I wanted to talk about was line trace. Yes. That I am not sure. I have no clue. Yeah, probably someone who works in numerical optimization, numerical, yeah. Okay, so coming back to this point, which I just briefly alluded to, that lot of times when we analyze the multivariate functions, we'll just rewrite them like this. So what I mean by this is the following. So you have f which is like this, okay, r into r. So as you will soon see in the upcoming weeks, so whenever you are in some space, you are at some point xk, you would want to go in some direction, okay? So wherever you are, if you are here, let's say xj, maybe you can move only along these directions. Okay. So the way we will denote this, the movement that is allowed, is by so the way we would look at the function in the vicinity of these xk's or xj's, we'll say, okay, whatever directions I'm allowed to move into, I'll see how far along those directions d. Okay, so each of these will be d1, d2, d3 and so on. Similarly here, d1, d2, d3, so on. So we would want to analyze the behavior of functions like this. Sorry, let me take that back. What I mean to say is, we have the function f and we are at some iteration xk. You'd be interested in computing derivatives and just looking in this vicinity of xk for this function f. So in general, what we will do is, we will just define g of alpha at this point xk as f of xk plus alpha d. So you fix direction d and point xk. You just look around a particular direction and you see for various step lengths. So this is then what will a lot of our theorems can be then rewritten in terms of this function. A good thing about this function is it's just a 1D function, so it's easier to state results in this term. So g is just R to R. Actually, it's a bit more specific. It's R positively positive, so alpha will be, the way we would define it is typically alpha is greater than equal to 0. So why I am saying this, so I'll just go through one or two more derivations and then I'll just restate our Taylor's theorem results using these scalar functions. Again, this is just to make life easy for us when we are doing calculations. So let's just compute the derivatives for this 1D function. So any idea how one can do this? Expand the function as it? No. So without any Taylor series expansion, can we say something? Yeah, it's just a chain rule. So what we'll do is, we have n dimensions, right? For f is going from Rn to R. So all that we have is partial derivatives. Okay, so maybe my notation is not so good. Let me use something else. So let's say x plus alpha d, and this is simply di, because alpha d alpha di. Okay, so basically this can be written as T transpose gradient of f at this. Is this fine? Yes. Yeah. So similarly, what we can do is we can now go on to define. So let me make a slight change in notation. So let me call this this gradient, which is del by del xi. Someone has joined. I hope you can still see my screen. Yeah, so let me just call these derivatives as rho i's. Okay, so del by del k. So what we can do is we can take a derivative of this now. So we can take derivative of this term. So it's going to, just by the same reasoning. So what we saw here, what we have seen here in this red box, we are going to do the same thing, but instead of the f, we'll have a partial derivative present there. So I will just be rewriting exactly in a similar fashion. So I'll just keep it here for reference. Del xk, yeah, that's fine. Okay, and times again the same thing. So here you have row k in question, and the indices are j. So what we'll end up getting here is dj. So just like we had I running here, for the same reason I'm taking the derivative for the ith component. So here again taking the component ijth component for this vector, and then taking derivative with respect to alpha. So we get the same dj. Okay, so what will be the double derivative? So we computed single derivative here. Similarly, we want to compute the double derivative, the rate of change at that point along this direction, using this scalar valued function. So what will that be? So we saw just now, so it's dk del by del alpha rho k so this is nothing but just rewriting it. It will be a double summation tk del 2 del xj del xk. So in general, by the way, this order xj xk, if I change the order, that matters, but here whatever functions we are dealing with, that's not a problem. So we can interchangeably write del xj del xk or del xk del xj. So the notation will be symmetric. So what does this look like? Does it look something familiar? Like something familiar? So it will be exactly this. Okay, so it's just the Hessian. This is just the Hessian. So this is just the Hessian at x plus alpha d. Okay. So this just offers us this compact way of writing things, because it is showing us that equivalently we can still use the same 1D Taylor series formulation approximations that we are used to. So what I am trying to say is g alpha, if you define as, so you are at some point x and you are looking along some direction d. Okay, let's just call it x prime. So we were seeing that, so g alpha will be nothing but g0 plus okay, something wrong with the eraser. Yeah, so alpha g dash 0 plus some residual term which is going faster to 0 than alpha. So what does this expression make sense? Have we seen this before? So if you recall, we had seen something like this. F of x plus alpha d is f of x plus what? Plus t transpose gradient f x plus something r of alpha. Is this not something we saw? Does it ring a bell? the way we had defined the Taylor series expansion around a point. Hello. So it's exactly the same thing. I'm just rewriting it like this. Not doing anything else. There should be an alpha here, sorry. So we had seen that at any point, it would be really nice if this had a laser pointer, but it doesn't. So this x plus alpha d, you just represent, you fix the x and d. We are fixing this. As long as the moment we fix this, then we can just freely move along this axis of alpha. I mean, just vary alpha and look at the function variations as the alpha keeps on changing. So instead of then having to write these clunky expressions, we can just rely on the 1D simpler expressions. So similarly, if you want a yes, alpha needs to be small, yes, to be able to apply the Taylor's theorem. I mean, the thing is, you are using the fact that function is continuous and differentiable. So you will have to accordingly choose the neighborhood. So alpha will be dictated by that. Yeah, it's just easier to write and handle things this way. That's the nice thing about it. I mean, you will later on see. Okay, let me not go there. Let me just stick to this. But I just wanted to say that it's a lot of times it's easier to just state our results in these line trace functions, especially when we are dealing with the multivariate functions. Okay. Especially, I think later on we'll do something for characterizing convex functions. So there we just effectively write in terms of these line trace functions and can easily prove our results rather than having to do the complicated vector calculus operations. Because ultimately no matter, a lot of times what you will see is you have equations that look like this, because you will be doing the Taylor series approximations. You will get similar higher order terms like this. So then you would want to probably you would want to compare these terms, you would want to take limits here of these multivariate functions. It's easier correspondingly to then just focus on these 1D functions, because there you can easily apply. I mean, not that we cannot apply here in the multivariate case, it just becomes easier for our calculations. You will see some result like for convex functions you need to have something like this, which is to say that if you have a bowl like function, you can always find some tangent, then the function will sit above this tangent. So to prove things like this, you can easily rewrite in terms of these g alphas and then prove these kinds of results. Yeah, he has not started. Yeah, he's not started yet. Okay, right. One more linear algebra question before we move to the Boyd questions. So the claim is there is a matrix M which is symmetric. This is given to us. It's symmetric and positive semi-definite. And it is given that for some vector v transpose mv is 0. Okay, this is given. these two pieces of information. And then we have to, then the claim is that V is 0. See, first of all, V transpose, okay, let me not use V because V is given here as some fixed vector. M is given to be positive semi-definite, which means X transpose Mx is greater than or equal to 0 for all X that are non-zero. So what can we say about, what can we say based on this information? Okay, so there's one more result which I have not proved, which if you want, maybe I can prove next time. So symmetric matrices are always diagonalizable. This is true. Try it out. If you are having any difficulties, let me know. Then do it next time. Okay. So what does this say? So M can be written as some UD U transpose. So here I think Soumyadeep, you were saying something, right? Something in terms of transposes. So we can write this for matrices like this, where inverse is the same as a transpose. Okay, so our X transpose Mx basically turns out to be X transpose UD U transpose X. So if you call this Y transpose, this just becomes Y transpose dy. Okay, so if we can choose X such that U transpose X is Y equals to some basis vector, meaning something like everything is zeros but only the ith place is 1, everything else is 0, and the rest is what I mean by the basis vector, standard convention. If this holds true, then what we will get is the corresponding diagonal entries, they will be non-negative. So that is all I can say about okay, M is symmetric, M is symmetric based on that alone, and the fact that M is positive semi-definite. So this is all I could infer from the fact that M is this. But okay, what else can I say? I'm given some vector V such that V transpose MV is 0. How do I utilize that information? Yes. But then what can we say? So okay, so now this was a digression. So this is what we know so far. So okay, M we can write as some UD U transpose. Okay, then, and we are given MV transpose MV is 0. How do we utilize this? Yeah, I think you're on the right track. So we'll need to do slightly more work, but yeah, you are right. We'll do something like that ultimately. So what we'll end up writing is D. Instead of this matrix D, what we'll end up doing is we'll define something similar. Call it D hat, and it's again a diagonal matrix. Okay, and all that we'll do is we'll just take a square root of this ith entry and call, and if there are non-zero entries of the in this di, then then so whichever are positive, we'll just take a square root there. We'll take a positive square root, otherwise we'll keep it 0. So it's like taking a square root, but then we'll only take square roots for strictly positive entries. Rest we'll just substitute as 0. So then what you can do is you can just rewrite this. Instead of ud u transpose, you can write ud hat d hat u transpose. Now what you are saying can be used. So v transpose mv. So what we can do is v transpose u d hat u transpose v. Okay, so this is z transpose, this is z. Okay, these are the two vectors. This is now norm z square. This is 0 if and only if z is 0. That's by definition of norm. Okay, so what does that, what is that? Yes, so d hat u transpose v is 0. What can we say now? It is here. Here it is for symmetric matrices. U is unitary. Okay, so all right, so here what we can do, we can just pre-multiply by ud hat, right? Right, so sorry, typo. So you have u d hat u transpose v equals to u d hat u transpose v. This is 0. So this is 0. Therefore MV is 0. So what have we gotten so far? M is PST and V transpose MV is 0 if and only if MV is 0. So I think I made a mistake now that I realize. That seemed a bit odd. Yeah, I think this would make more sense. I have not given strictly positive, so fine. So this happens only if the V vector is in a null space of M. So sorry about that. It's not realized. Okay. Any questions? Yes. Yes. Yeah, actually, I personally don't know how to prove that. I have never tried it. I have to check that. I'm not sure. Also, there are too many theorems called Minkowski's theorem, so bit confusing to which one. Yeah. Yeah, it's possible it could be under a different name. I have to check. Just send me a message in case I don't get back to you about this. Yeah, yeah, yeah. Okay. Any question from the material? Otherwise, we can move to some questions about cones, convex sets, and this week's assignment questions. Any doubts from the lecture material? Yes. Yes. So if it is the same set, then it has to reduce, right? Which transformation may lead to it? I'm not sure if there can be a guarantee on that because the set can be anything crazy. But if you are writing the same set in different ways, but there has to be some way to relate the two set transformation, right? If it's the same set, I don't know if am I making sense? Yeah, so just going back to the block example that he gave, no, where x was in a 2D plane, the set is two dimensional, and both. So we are considering this block where it's basically the square is going from -1 to +1 on the x-axis and -1 to +1 on y-axis. So it's just a square, a box centered at origin of length 2, right? So I mean I can always define it as just those intersection of those four hyperplanes, but like you saw, I could always define it in this other complicated way. So I don't know if you can characterize it for any arbitrary set. That I really doubt. Uh, hmm. So I'm just thinking, instead of a square, you can just take any other polygon. So what in that case, what you can do is, again in the 2D case, and again I'm also thinking out loud. What I'm thinking is, if you have a case like this, and let's say this part inside the diamond and the boundary, they are all included. This is my P, let's say. Then there are many ways to define it, right? Mod of x1 plus mod of x2 less than equal to 1 is one way to do it. Isn't that correct? But then I can also write it as intersection of this hyperplane. Oh well, this is the same thing. Okay. What should I say? Let me see. Is there any other representation for this? What I said is the same thing. Not sure actually. Is there any other representation for this case? x1, x2 less than equal to 1. That is one way to do it. Oh yeah, correct. So yeah, sorry, I don't know why I'm getting confused. So here I mentioned specifically only this region, right? Less than equal to. But I could. What else can I say? Sorry, just a second. Let me think out loud about this. Meanwhile, yeah, if you have any thoughts, please pitch in. So I have a diamond here that I could possibly specify in different ways. So one is hyperplanes intersect. I think that I've already written here. Okay, so I think maybe I'm just overlooking the fact that this fact is a nonlinear function, right? Yeah. So but I can then rewrite in terms of the individual hyperplanes, no? Removing the mod. So then I have alternate representation, right? So what I'm saying is, in this case, it's non-linear. I remove the modulus. I take into account all the sign x1 plus x2, x1 minus x2, minus x1 plus x2, minus x1 minus x2 equal to 1 or less than equal to 1. Then those are all these corresponding hyperplanes, right? So then I have found two alternate representations for the same polyhedron, right? Polytope specifically. Yeah. Does that help? Okay. So yeah, that will come into the context of linear programming. Yes, I think you would have seen him allude to that when we are trying to solve the optimization problem, linear program, and it boils down to saying, okay, find that, just go through the list of extreme points and then find the minimum value. So yeah, I think maybe that's the intention of the comment or in the book. Okay. Just give me a second. Yeah, just putting it for charging. Give me a moment. Okay, so if there are no questions about the class material, then what we can do is we can solve some questions. So would you people like to solve some questions about some basic first order, second order necessary conditions as well, or just directly move to the questions about definitions of convexity, cones, convexals, affine conicals, and so on. Okay. Yeah, okay. Anyway, let me just get started. So I will start with something about okay, let's start with something very simple, which is so let's say there is a ball centered around some point x0 with radius r. Okay, just writing it informally here, but you get the point. Is it convex? Is this ball convex? But how do we prove it? Yeah, that's it. So what we do is theta x plus 1 minus theta y minus x0, or you can just write as saying theta x minus x0 plus minus theta y minus x0, and then just use triangle inequality. Right? So this basically I wrote theta plus 1 minus theta times x0. Okay, this was pretty straightforward. How about the following question? So we said that there is the question 2 is about convex hull. So we define convex hull of a set of the points x1 x up to xm as this combination. So if the points are in Rn, any convex combination, if we take all those points, it is called convex hull, and the alternative definition is intersect all A such that xi belong to A for all I, and A is convex. So intersect all such A, meaning the smallest convex set. Smallest meaning take intersection of all such convex sets. Smallest convex set containing x1 to xm. Yeah. So before we even say that the purpose of this exercise is to ask whether these two are equal or not, because I just told that this is equal, but why should we accept that? Yeah. Ultimately, if you want to do analysis, it is this one that helps. So maybe what we'll do is I'll just call this as P, and I will call this set as Q. Okay, this representation is P, this representation is Q. The question is P the same as Q? That's the first question. After that, maybe we could ask which one is more useful. Generally, you would want to use this property. X is a convex combination of this, but then if you recall from the last week's material, you don't know what that M is. because here I have given you specifically some points M, but in general you would have convexal of a set S where you are not given that S is only these points. So what I'm saying is S need not be just x1 to xm. In that case, finding such finding such xi's, how many of xi's should I pick up from this set S so that I can generate my x, then that becomes a bit of a problem. So each one has its own problems, whichever representation you pick, but they are both equal. So yeah, is P equals to Q first of all? I mean, I just said that it's equal, but why, if and why, whichever answer you pick. So how do we prove? How do we go about proving this? If you want to prove both sets are equal, let's just Right. So what we want to do is we want to say P equals to Q. So we'll split it into two. We'll say P is a subset of Q and Q is a subset of P. We'll see if this holds. Then we can say that P and Q are equal. So like you pointed out, let's take an element P in P, and since P is in P, there exists some theta I prime such that P can be expressed as a convex combination of these xi's. Okay, so does this P belong to Q? So remember this. Okay, so be a bit careful here. So what we need to say is, first of all, xi's belong to S. So S, by the way, is just a set of points x1 to xm. So let me erase this in case this confuses. For our case, the set that we are given is just this m points, this set of m points. So these m points, now we by definition we said that A is convex such that xi's are contained in A, and A is convex. Xi is in S. This means xi is in A. A is convex. This implies any convex combination has to be in A. Right? So this implies there is at least one A, convex A, containing these points, which also contains these convex combinations. So that means this convex hull that we have defined through this representation, the P, this is a subset of Q. Right? So for any P in P, we are saying P is also in Q. This implies P is a subset of Q. So what else can we say? So how do we prove Q is a subset of P? So Q is again this smallest convex set containing x1, xm. See, again the same thing. So you take an element Q in Q. So remember that Q is an intersection of all the A's, all such A's. So that means Q belongs to all such A's which are convex, contain S. So what can we say about this? What can we say from this information? There is an element that I pick from this set Q. Let's call it small q. This has to be, by definition, it has to belong to all such convex sets which contain these points xi's. So what can be said from there about the membership of Q in P? But why is that? I mean, any convex combination, that's the definition of P, but why should Q have to be in P? Yeah. Okay, so the focus here is on this intersection, right? It's the way we have defined it. So is P one of the A's here? Does P satisfy this property that P is convex and P contains all the points xi's? Is the question clear? Okay, so what I am saying is P, the set P that I have defined here through this convex combination, is it a convex set? That's okay, but so if from this definition I am saying, the setting aside the way we've defined other things, I'm saying just by what I've written here, it's a convex set, right? And does it contain all the xi points, all the xi's? I can just set the corresponding theta I to be 1 and rest as 0, right? So all the xi's are contained in P. So that means P satisfies this property that A is convex and contains the points x1 to xn, right? So what we are saying is P is also one of these A's. That's all we need. So Q, if there is a Q in Q, then Q is in A for all A's. Hence Q belongs to this set P. This implies there exists some theta I primes, double primes, such that Q is summation I theta double prime xi, such that summation I theta I double prime is 1, theta I double prime greater than equal to 0. So this implies Q is a subset of P. So we are done. Is this okay? Alright. So let me now move to the Boyd questions. This is also, by the way, one of the Boyd questions from chapter 2. So let's look at a few more questions. This is Boyd 2.1. How much time do I have? Just a second, I'm opening the assignment. So yeah, maybe let me put the question and then meanwhile search for the rest of the questions. Oh, okay, got it. Yeah. Okay. So the question is, we have. By the way, if you have solved these questions, just let me know so that I can skip to the rest of the question. Because there are a lot of questions that we can solve. If you've already seen it or solved it, we don't have to discuss it here. So there is a convex set C. Okay, and let's say there are k points x1 to xk in C, and let's say define the corresponding theta 1, theta k such that they are greater than 0, and summation theta I equal to 1. So we have to show that theta 1 x1 plus theta k xk is in C. So okay, first question, do we have to really show this? How did we define convexity of in a set? Right, yeah. Yes, yeah, so yeah, good. So that's the thing, right? We need to say that for any k, we have a such a combination that also is in the convex set, but we still need to show it. So how do we do that? Okay, and so how will we do that? So k equals to 2 is true by definition, right? Yeah, just a second. Something wrong with the tablet. Can you see my screen? Okay, yeah, sorry. So, okay, k equals to n, you are saying, let's say induction hypothesis. So, which means x1 to xn in C, and so theta 1 xn, theta 1 x1 plus theta n xn is also in C. Standard conditions. Okay. And theta I is greater than 0, summation theta I is 1. Looks something wrong with the tablet, not reading properly. Maybe the one not app is. So k equals to n plus 1. This is our induction step. So how do we do that? Yeah. So let's just start with what we are given. So here also, wait a second. Yeah, okay, let's start with this then. So theta 1, theta n plus 1 greater than equal to 0, and summation. Just a second, let me check if it's still recording. Yeah, okay. So and then this is given to us. So how can we use that? So let's call this point y, so that you people can maybe point out things with a bit more ease. Plus 1 theta I x I. So this is summation equals to 1 and plus 1, sorry, theta plus 1, we have x and plus 1. Okay, now what else do we do? Okay, so 1 second. So you are saying this thing belongs to C. Okay, fine. Right, right. Okay, so so note that whenever you define convex combination, it has to be like this. But here we don't have that, do we? That's okay, but so what's the relation? See, what I am trying to say is, see, y equals to, what should I call it? Let me call it w. This element that you are seeing here, summation I equals to 1 to n theta x, is w plus theta n plus 1 xn plus 1. We can't say anything about this, right? We need a form like this. Yeah. Yeah. No, you're right. Induction is one way to do it, definitely. Just have to be slightly careful about the terms, that's all. So, just without loss of generality, what you can do is, can assume theta n plus 1 is, I want to assume on theta n plus 1. Yeah, it doesn't really matter. I mean, you can pick something else also. Okay, but I'll just, for now, I'm assuming theta n plus 1 equals not 0. You can pick some other index and you can do an equivalent calculation. So, I'll do this. Okay, sorry, not equal to 1. So what I'll try to do is I will one minus theta plus 1 theta I 1 minus theta n plus 1 xi plus theta n plus 1 xn plus 1. Let me see if this makes sense. So here you have 1 minus theta n plus 1 times summation I equals to 1 to n theta I 1 minus theta n plus 1. This whole thing, by the way, is just summation I equals to 1 to n theta I just used this information that is given to me. I write xi here. I have theta n plus 1 xn plus 1. So again, let me use a different color. So I have theta times some vector xn plus 1, and I have the 1 minus theta, the same theta, times, what about this whole term? So belongs to C, right? So is it fine now? Now is it in the form? So here theta n plus 1 mu plus theta x n plus 1. This is in C, this is in C, this is theta n plus 1. So yes, yeah. So rescale, because we have to ultimately be able to apply the definition of convexity, and other than that we can use the induction hypothesis. So we have to rescale it so that we can get a form like this. So once you rescale, it is okay, because by induction hypothesis the remaining terms will sum up to 1 and give you what you want. Not sum up to 1, but they will be in the set C, and then you can proceed with the proof. So by the way, in general, just the fact, this is not relevant to this, but in general, if you have a closed set, right, and let's say so C is a closed set, just a digression, like if you have an element in C, x, okay, and you want to find the sequence converging to x in C, how will you find it? This is lot of times very important. You would want to construct these sequences, exploit this closure property, and show convergences. So again, this is the one way that I know. Maybe there are other ways of doing it. So we will stick to the 1D case, but in general you can do it in any Rn. So what you can do is, so we know we are given x, okay, and what we'll do is we will just take any x n, pick xn for all n such that xn minus x is less than 1 by n. The claim is that sequence xn converges to x, and why is that? It's simply because you pick any epsilon greater than 0, then by Archimedean property there is some integer such that if you multiply it with epsilon, you will get n epsilon time is greater than 1. So what does that mean? It means xn minus x less than 1 by n is less than 1 by n, capital N, which is less than epsilon, for all n greater than or equal to n. This is precisely the definition of convergence of sequence. Okay, just wanted to point that out since you are on this topic. Okay. Uh, which property? I mean, I can put a metric there. It doesn't have to be necessarily Euclidean space, but any metric space, I can, instead of the xn minus n, I can put d of xn. Yeah, yeah. Maybe slightly geometric question. This is 2.5, and after that we'll just move on to the assignment questions. So you have two parallel hyperplanes. A transpose x is b1. So this is h1, and there is another hyperplane which is parallel to this. A transpose x equals to b2. So what is the distance between h1 and h2? How do we find this? So I'm given h1, although that they don't look parallel. Sorry about the drawing, but we try and make a parallel. Yeah, really bad. So you have h1, h2, and this is the normal A, right? This is the minus A direction. So yeah, what do we do? What is the distance? Okay. Right. So you take any point on x1, h1, and any point on h2. That's the first thing you suggested, right? Okay, so when you say, okay, so maybe let me use a different color. So let's say the point is this here, that is x1, let's say, and let me use a different color. Let's say this is x2. Okay, then so okay, I don't think I understood. So you want to project this point x along here or along here? Project along the normal. Any segment that joins x1 to x2, but this is longer, no, than, let's say, this distance. See, are you saying this point here? Okay, but okay, fine. So yeah, the correct. I mean, that's the distance, yes. But how do we find that? So if you have x1, x2, so what are you suggesting we do? So when you say project on the normal, you mean to say just take a inner product, right? So that is basically saying A transpose X, which is nothing but sorry, this is not B2, this is B1. So A transpose X is already given, right? B1 and B2. So I'll just slightly rephrase what you said. So it's because it's parallel, because these two hyperplanes are parallel. What we can do is, 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 what we can do is Yeah, so what we can do, so this is A transpose X is B2, transpose X is B1. So let's say we just want to take this point which are exactly below or on top of each other. Okay, let me call this X2, we call this X1. So you were right about one thing, which is that I need to look around this normal direction. So all I need to now do is x1 will be some lambda 1 times a, and x2 will be some lambda 2 times a. So my distance will simply turn out to be lambda 1 minus lambda 2 times norm of a. So far so good. Hello. Yeah, so how will you find lambda? So we want A transpose x1 is p1. X is lambda 1 a1. So lambda 1 A transpose a equals to b1. Okay. So we have lambda 1 is b1 by norm a squared. Similarly, lambda 2 is b2 by norm a squared. So what is the distance between the two hyperplanes? Is exactly this x1 minus x2. And what is it? It's p1 minus p2. Take a mod of that. The norm squared. And there is another norm. So this will get cancelled. So ultimately it's saying, as you would expect, just subtract the two terms p1, p2. Just normalize it. So this is our answer. Yeah. So there is a norm square here. Yeah. Okay. Any questions? Okay. Yeah, so I mean, there are a lot more questions that we can keep on solving. I don't mind that we can pick a few every week's discussion and see what all we can cover. But one of the things that I have to do as part of this course is to look at the questions that are given to you people for your NPTEL assignments. So let's just take a look at those questions. Okay. Okay, so this is the week 5. I am not sure, Shamili, because I'm just conducting the discussions. I'm not an official. I mean, there are other TAs who will be actually helping set up conduct the exam. So I'm not sure about that. Yeah, I think it will mostly be multiple choice because otherwise it's difficult to evaluate. I don't. Yeah. So this is an obvious question, I hope. So is this a polytope? Is this set a polytope? So if I just draw this box, it's a polytope, right? It's bounded. How about this one where you have just a line, so meaning a hyperplane? Is it a polyhedron? So what we are given is, we are given this line. Is this a polyhedron? Yeah, so intersection, yeah, so yeah, you are right. So you have x1 plus x2 less than equal to 1, x1 plus x2 greater than equal to 1. So yes, there is a set which is again R2, x1 plus x2 less than equal to 1, x1 x2 is greater than equal to 0. So we basically this set. So what are the extreme points here? Yeah, so simply okay. Okay, what else do we have? Again, S is x in R2, x1 is x2 squared, meaning the first coordinate is the square of the second one. Is it a cone? So it's saying x equals to y square, or y square equals to x. So is this a cone? Why is that? Ah, okay, 1 second. So you are saying x2 square x2. Okay, so let me maybe just use a different symbol. So let me say z comma z square. Okay. Sorry, z square comma z. Sorry, yeah, z square. Yeah, right. Correct. Yeah. So to put it simply, you can just take 1 comma 1, and let's say you take theta as 2, then 2 comma 2 does not belong to S. You're right. Okay. Question 5 is 7x plus 13y. It's a line. To minimize such that 5x plus 2y is 1, x plus 3y is greater than 2, and x greater than equal to 0, y greater than equal to 0. Is this in the standard form? Okay, so standard form will require what, or what for us? Actually, let me check now. I forgot. Well, what he is referring to as standard form, let me just confirm that if it is what I think it is. Standard form means, okay, so just to refresh our memory, especially mine, minimize C transpose X such that AX is B and X greater than equal to 0. This is our standard form where A is full row rank and obviously B is greater than equal to 0 because an equality constraint. So how about this? So this is the problem, right? Here. Correct. So it's not because of this reason, right? Okay. So again you have minimize 3x plus 2y. I think this is also about okay, this is about converting form. Okay, let me just write this question first. So this is the problem that we are given. 3 minimize 3x plus 2y. And there are some constraints that are given. So can we convert this to standard form using only one slack variable? Yes, no. Why is that? So this is already an equality constraint, right? This is greater than, yeah. So this is fine actually. So this is okay. This need only one. Right, so this is, yes. So question 7 is, I think they are all very similar. We have 4x plus 2y. Three x plus 5y plus z is 2. 3y plus 8z is 7, and x, y, z are all non-negative. So how many additional variables, slack variables, are required to convert this optimization by this LP into a standard form? Yeah, none, because it's already in standard form, right? So this is fine. Equality, and all the inequalities are simply these orthogonal constraints, so it's already in a standard form. Generally yes, because if you recall, so this is something that we'll see in the coming lectures, that if you formulate your problem, I think I deleted that, let me just make a note here. So whenever you write your feasible region for linear programs as this equality constraint with this orthogonal constraint, you are guaranteed to have at least one extremum point, at least one. So if you just write, if we instead just write it as minimum x C transpose x A transpose x less than equal to b, this one may or may not have that extreme point, but the way we put this constraint on the orthants, that kind of helps us ensure that when we formulate it like this, there is at least one such point, and hence we at least there is some hope of finding the solution. Yeah, it's just because of this reason. Yeah, in a way, yes. Still, there are many other problems. For example, you can keep on going searching for extreme points. There are many issues. It doesn't stop here, but yeah, at least this ensures that by the very formulation we are guaranteed to have at least one extreme point. So hence there is some solution. Okay, let me do one more check if it's fine or not. Okay, recording's going good still. So we started at 3:05, so I have about four more minutes. So we'll be done with the questions by then. Oh, okay, I see. I did not realize that. Okay, yeah, thanks for pointing out. Yeah. I think there is some issue with the tablet. I couldn't make it work with the iPad, so I'm still using the. Yeah, hopefully next week I can figure it out. Okay, all right. So let's see the next question. This also, well, you have seen, so in a way you know the answer to this question, but let's just see if you recall. If optimal solution of LP exists, so if optimal solution of an LP exists, it has to be unique. Is this true or false? Okay, so can we prove this somehow? So again, this is just a sketch, but we can make up examples which do exactly this. So let me draw a polyhedron. So this is my. So let me still complete the drawing. Let's say that this is my C transpose X equals to K. Okay, and K decreases here in this direction. So when I come here, with this red line, this entire segment, optimal solution set, is it fine? So in general, it doesn't have to be the case that it's unique. If there are multiple, so what I'm trying to say is, if there are multiple extreme points with same optimal value, then any convex combination will also be optimal, right? So I think one simple way to cook up an example would be to minimize y such that Yeah, I think you can just take a very simple case where you have x plus y less than equal to 1 and x and y are greater than equal to 0. So you have this green region, this is your feasible region. So let me maybe call this P. Okay, so here if I say minimize y, so my y would be something like this, some line like this. So how what will be the minimum value in that case? Hello, is the question clear? So this green region is my feasible region, and this y, this y equals to some constant, that is my contours. So what will be the minimum value in this case for this feasible region? So what are the extreme points in this case for P? Right, and for us the relevant points are, for relevant extreme points are which ones? Yeah. What is the minimum value of y that can be taken? 0. So which points will correspond to that extreme points? Yeah. So these two are relevant, right? So then any combination then in turn also makes sense, right? Any point here also has optimal value, isn't it? Okay, I'm almost done. Just 3 more questions. So yeah, we'll just, sorry for the few slight delay. We'll look at these 3 questions and we can end the session. So minimize C transpose X. So again we are looking at linear programs. This is the standard form. And the question is, so X star and X double star are optimal for this problem. Is 2 by 3 X star plus 1 by 3 X star star also optimal? That's the question. Yeah, so actually in general any theta X star plus 1 minus theta X star star will work, right? Theta X star plus 1 minus theta X star star. Yeah, we'll come to that. I mean, there are many ways to do it. I think he will cover at least 1 or 2 ways to do it. So this, by the way, it's clear, right? You just put C transpose X star, sorry, theta X star plus 1 minus theta X star star, and because the optimal values are equal, we can just say theta plus 1 minus theta times the constant, whatever F star is. So that's why we are getting the same optimal value. So I hope that part is clear. Okay, last 3 questions. We have a system of equations Ax equals to b. There are 8 variables. A is 3 cross 8. Okay. And the question is, if x prime happens to be 1, 2, 3, 5, 2, 6, 0 0. This is a 8 cross 1 vector. Then x prime is a possible basic solution. Is it true that this can be possibly a basic solution? Any thoughts? Okay, so what do people remember the definition of what is a basic solution? Hello. Okay. So thing is, because we have A as full rank, in general what we will do is we'll just decompose the matrix, not decompose, but we will write the matrix into these rearrange the columns, and we will write it as the following stack. These are all linearly independent columns. These are the remaining columns. So when we solve Ax equal to 0, equals to B, instead what we will end up solving is A. So what we will end up writing is Pn, and then we will break the x also in corresponding parts. X basic xn is equal to B. Okay, and we will just, for simplicity, this won't matter because these are linearly dependent, so we'll just take it as 0. So what we will end up getting is xb is B, and because B is invertible, these are all linearly independent, and A is full row rank. So B will be a square matrix. So because B is invertible, this basic solution is basically saying B inverse B. Take all the linearly independent columns of A, make a matrix out of it, take an inverse of that, and just multiply it with this vector B, and that's going to be your XB. So this XB, if this happens to be greater than or equal to 0, which is the constraint for our standard formulation of LP, then it is called a basic feasible solution. What we are as of now asking is this X prime a basic solution or not? Possible basic solution or not? Is the definition clear? Because right. So okay, so the point to note is that A, if at all, it has to be a basic solution first of all. So A, we would want at the rank that A can have is at most 3. So let's say that A has rank 3, full row rank. In that case, because this XP will be the basic solution that corresponds to this matrix P, which will be a 3 cross 3 matrix, you would expect to see at least 5 zeros for it to be even considered a basic solution, possible basic solution. Does that make sense? Yeah. So that's the point. Okay, so it's in a similar spirit. I think there are just the last 2 questions, and we are in the same setup. Ax equals to B. X is in R8. In A is in R2 cross 8. Also B is basically vector with 2 components. The question is, what is the maximum number of basic solutions of this system of equations? maximum number of basic solutions. So again, just remember what we need is, let's say A is rank 2. So we need to have at least 6 zeros in our X. So that means, because here you are asking maximum number of basic solutions, so we will limit it to 6, and hence what we have to do is we have to have 8 C2 combinations. Is it fine? Okay. So for the final question, you have A, so and then you have X, and you have P, X equals to P, 10, 3. So they are given options. Which of this is a basic solution for our system AX equals to B? So 18 by 11 minus 9 by 11, 1. Right, so just a second. So okay, one thing that we can immediately observe is this is a 2x3 matrix. So that means X will have at least one 0 component. So that means A and B are not possible, right? So we are left, sorry, A and B, not C. C and D are the only possibilities. One more thing is, okay, so D unfortunately doesn't satisfy the constraint Ax equals to B. So in that sense, only C is the possible answer, although that doesn't have to be. So we'll still check. Okay, so D is not possible because A times 0, 1, 5 is not B. Okay, so regarding C, think like you said, we'll have to check. So the column 1 and column 2 of A are 6, 1 and 1, 2. So they are linearly independent, right? So hence this C is a basic solution. Okay, so yeah, so we have covered the assignment 5 questions, and we did look at a few other questions from the Boyd textbook. I think we can continue doing this if you people are interested. Not necessarily from Boyd, but yeah, some more questions, because assignment questions won't be typically so lengthy or involved. So we can stop here. So yeah. Okay, yeah. So let me first stop the recording.